Hello everyone, I'm Sister T and I'm super excited to be the speaker of AP Mechanics C. First, we will have a brief review about the last video and we will have a further discussion on GPE, conservation of energy, and EPE. Okay, so let's get on to the business. First, let's take a look at those two concepts you must be familiar with, right? So for conservative force, the force done by it has nothing to do with the path that an object travels, which means, the tracery is not important at all. Examples include gravity and universal gravitational force, and for non-conservative force, it's the opposite. Tracery really matters. It's really important. And examples include kinetic friction. Okay, and here are two equations that we also covered in last time's video. We'll still use them today, so I hope you remember. Okay, so the first concept I want to talk about is the definition of GPE. Like kinetic energy, it exists because of the motion of the object, right? And for GPE, it makes the same sense. It exists because of a specific force, which is gravitational force. For example, if I'm trying to lift this box to point A, let's first draw a three-body diagram. Ignore air friction and stuff. It experiences a gravity pointing downward with a magnitude of mg, right? And an upward force, let's name it Fex, exerted by us. Okay? So how we are gonna find the work done by the gravity, mg? So while we are lifting this box, the direction of displacement is upward, right? But it's the opposite direction of Fg. So we are doing a negative work. And since we know that it equals to Fd multiply cosine theta, in this case theta equals to 0, so it's 1. And let's just plug number in. Don't forget the negative sign, since they are in different direction. In this case, d equals to h, so I will just write h. Okay, so remember this. Let's think of another situation. For example, if I hold the object that I have elevated to point A and let it experience a free fall, so it is initially at rest, and we determine the downward side as the positive side. According to Big Five equations, we have this. And we can write it as this in this case. So, when we release the object from point A until it strikes the ground, it will achieve a kinetic energy with this, right? And equals to the value of mgh. So from this equation, we can associate with this. So how much Ke the object gained is actually the work that we do, right? And the work is clearly associated with the height of the object. So that helps us to come up with the definition of GPE. We usually use U to represent it, and you can see it a lot in the AP exams. It can also be understood as the stored potential energy in an object by elevating the object to a height h. It is actually the ability of the object to do work at a certain height. For example, I released the object at point A and I was able to do this much amount of work to attain this, right? Okay, so in this case, we actually see shadows of conversion between energies. We will have a closer look about this. So still the same example, And when it is initially at rest, let's talk about its Ke and Pe. So Ke should be 0, right? And Pe should be mgh. When it falls down to the ground, it was able to attain a kinetic energy of this, and Pe becomes 0 because we set this as the 0 line, but actually you can set it on your own, depends on the situation, okay? Because we need a system to calculate the height. Okay, so we can see that the increment in kinetic energy actually equals to the magnitude of how much Pe is lost. So we can yield this equation, and it is actually very similar to the idea of conservation of energy. At least I think so. I think conservation of energy is actually multiple steps of conversion. If that can help you to think, so it stated that if only conservative force acting on the object and Ke1 plus U1 equals to Ke2 plus U2, which means the mechanic energy of the object is conserved. Okay, so you really need to remember that, and you will see many examples like this. For example, a roller coaster or a wavy mountain, and it will give you many points like A, B, C, and it will give you maybe an initial energy, and it will ask at specific points like how much, what is the velocity at that point, and that's when you need to apply that rule, conservation of energy, to this. But in the later chapter, the momentum chapter, and we will also encounter situations, collisions specifically, that do not obey conservation of energy. We will cover that later. Okay, so the last point I want to discuss is EPE. Now we have a spring, right? And the first point that I want to emphasize is this question: which one? You see, if I want to compress this object, here is the 0 point is the original length, okay? The original length of the spring. Okay, so if I want to compress the object to here, and this is my hand, okay, so the force that I exerted to the spring is pointing this way, right? And at the same time, the spring will give me a force with the same magnitude but pointing at different direction. So there are actually two forces. So who applied the force to whom is a question that you need to consider. And you know that since if I remove my hand, the spring will bounce back to this direction, right? And during this compression, let's see the direction of displacement. When I compress the object to this direction, displacement is pointing to the left, right? But Fs, the force exerted by the spring, is pointing to the right. So for forces that have that feature, we call them restoring force. Okay, so to have a closer look of the relationship, we need to know about Hooke's law. It can be written as this. I will use the force exerted by our hand. As you can see in this equation, K represents the stiffness, or in short, spring constant of the spring. It is usually given, but the question may also want you to find through a graph or something like that. Okay, so when we find the force, we can see through this equation that F varies with as x changes, right? So how are we going to solve that problem? We need to find a determined F, right? So in order to simplify, we calculate an average value of F. This graph may help you to understand. So it equals to 1/2 of kx. And in order to find the work done by it, it will equals to this, right? And the work is what the spring will do after the hand is removed. And for Fs and Fex, it's just the forces that have same magnitudes but with different directions. And you can also use the same idea that we use in here, right? That the work done will probably done by the spring is also the potential energy stored in it. And I'm sorry, my iPad looks bad. It works for a long time. Okay, so that's all for today's video, and I actually leave a little question for you guys, and I want you guys to find where specific values of those quantities exist. For example, it's the original length, and when the velocity, for example, velocity will reach its maximum, minimum, or zero. Okay, we will cover that part in next video. And you can leave your comments on our different platforms. We will check, okay? And thank you really much. And thank you very much. And I hope you guys enjoyed this video. See you next time. Bye.